Introduction to Organic Chemistry. Petrol in your car, the medicine in your cabinet, the plastic in your phone case, perfume, the protein in your muscles, and the DNA inside every one of your cells. What could all of these possibly have in common? Take a second. The answer is one single element, carbon. Every one of these is part of a subject we call organic chemistry. And by the end of this video, you'll understand exactly what that means. Let's go. So here's the definition, and it's simpler than you'd expect. Organic chemistry is the study of carbon compounds. That's it. Originally people thought these compounds could only come from living things, from organisms, which is where the name comes from. We now know that's not true. Some organic compounds occur naturally, like the sugars in fruit or the proteins in your body. Others are synthetic, made by chemists in a lab, like most plastics and medicines. One more thing to lock in early: almost all organic compounds are covalent compounds. The atoms share electrons rather than transferring them. Keep that in your back pocket, it explains a lot of their behavior later on. Now the big question: out of every element on the periodic table, why does carbon get a whole branch of chemistry to itself? Two reasons. First, carbon has 4 outer electrons, so it forms 4 covalent bonds. We call that tetravalency. 4 bonds means carbon can connect in 4 directions at once. Second, and this is the magic, carbon atoms can bond to other carbon atoms, over and over, forming long stable chains. That property has a name: catenation. Because those carbon-carbon bonds are strong, the chains don't fall apart. So carbon can build straight chains, branch chains, and even rings. Mix and match those, add a few other atoms, and you get millions of different compounds from essentially one element. That's why carbon is the backbone of organic chemistry. Let's organize those shapes. Carbon structures split into 2 categories. Open chain compounds, where the carbon chain has 2 ends. These come in 2 flavors: an unbranched chain, where carbons run in one line, and a branched chain, where a side group hangs off the main chain. Then there are cyclic compounds, sometimes called closed chains, where the carbons join up into a ring with no ends at all. Carbon and hydrogen are the headline act, but organic compounds can contain a few other elements too. Oxygen, nitrogen, sulfur, phosphorus, and the halogens. That's fluorine, chlorine, bromine, and iodine. Here's an idea that unlocks the whole subject. Most organic molecules have a special reactive part, and that part is called a functional group. The exam definition to memorize: a functional group is an atom or group of atoms that determine the chemical properties of a compound, or, more precisely, of a whole homologous series. Think of the long carbon chain as the body of the molecule, and the functional group as its hands, the part that actually does the chemistry. When a set of compounds all share the same functional group, they form a family, and chemists call that family a homologous series. A homologous series is a family of similar compounds with similar chemical properties, due to the presence of the same functional group. There are 5 characteristics worth knowing, and these score marks. Members of a homologous series: 1. Share the same functional group. 2. Share the same general formula. 3. Differ from the next member by 1 CH2 unit. 4. Show a gradual trend in physical properties, like boiling point. And 5. Have similar chemical properties. Same group, same formula pattern, steady step in size. That's a homologous series. Let's see a real homologous series in action: the alcohols. We start with methanol, 1 carbon, plus the hydroxyl group. Add a CH2, and we get ethanol, 2 carbons. Add another CH2, propanol, 3 carbons. One more, butanol, 4. Notice what changed and what didn't. The chain got longer by 1 CH2 each time, but the hydroxyl group never moved. Same functional group, all the way down. That's exactly why methanol, ethanol, propanol and butanol all belong to one homologous series, the alcohols. There are 3 different ways to write the same molecule, and exams love to test whether you can tell them apart. Let's use ethanol. First, the displayed formula. This shows all the atoms and all the bonds, drawn out fully. Nothing hidden. Next, the structural formula, a shorthand that's still unambiguous, but tidier: CH3CH2OH. It tells you exactly how the atoms are arranged without drawing every single bond. Finally, the molecular formula, just the count of each atom. 2 carbons, 6 hydrogens, 1 oxygen. Same molecule, 3 levels of detail. Once a family follows a pattern, We can capture the whole series in one expression, a general formula. The letter N just stands for the number of carbon atoms. For alkanes, it's CnH2n plus 2. For alkenes, CnH2n. For alcohols, CnH2n plus 1OH, and for carboxylic acids, CnH2n plus 1 COOH. Plug in any value of N, and out pops a real member of that family. Now to a word you'll see everywhere, hydrocarbon. The definition is right there in the name, hydro for hydrogen, carbon for carbon. A hydrocarbon is a compound made of carbon and hydrogen only. Nothing else. No oxygen, no nitrogen, just C and H. Crude oil, petrol, natural gas, all mixtures of hydrocarbons. So if you ever see an oxygen lurking in the formula, stop, that is not a hydrocarbon. Hydrocarbons themselves come in two types, and the difference is all about the carbon-carbon bonds. On the left, alkanes. Every carbon-carbon bond is a single bond. Because they can't fit any more hydrogen on, we call them saturated. On the right, alkenes. They contain at least one carbon-carbon double bond. That double bond means they're not full up, so we call them unsaturated. Watch the difference directly. Here's ethane, an alkane, single CC bond, saturated. Now remove two hydrogens and pull the carbons closer, a second bond forms between them. That's ethene, a carbon-carbon double bond, unsaturated. One bond versus two, that single change is the whole distinction. Let's tie it all together. Organic chemistry is the study of carbon compounds. It all rests on carbon, because of tetravalency and catenation. Carbon's reactive parts are its functional groups, and compounds sharing a group form a homologous series. We can describe any molecule with three formulae, displayed, structural and molecular, and capture a whole family with a general formula. Compounds of carbon and hydrogen only are hydrocarbons, which split into saturated alkanes and unsaturated alkenes. That's the entire map of this lesson, one connected picture. Before the quiz, two mistakes that cost easy marks. 1. A functional group is not the same as a homologous series. The group is the reactive part, the series is the whole family. 2. A structural formula is not the same as a displayed formula. Displayed shows every bond, structural is the shorthand. Lock those two in and you're ahead of half the candidates. Time to test yourself. 5 quick questions. Pause the video after each question, and try to answer it before continuing. How many did you get? And that's your foundation in organic chemistry: carbon, functional groups, homologous series, the three formulae, and saturated versus unsaturated hydrocarbons. If this helped, give it a like, subscribe so you don't miss what's next, and come straight to the next lesson: naming of organic compounds.